Hello, everyone. Good evening. It's nice to meet you this evening. And yeah, so fortunately, last week we were not able to meet due to some few challenges we had, but we are back this weekend. And this weekend, we're focusing on Pytorch classification. So primarily in this particular week, you'll be learning what is classification, how can you use deep neural network for classification. And the learning outcomes will be like classification in general and the effects of activation functions. So we will just get started in, yes. So as always, we'll keep using like this notebook for all our tasks. So this is your main resource for this particular cohort, and which looks at, so in this particular notebook, we'll be looking at classification. So in general, like in machine learning, there are different kind of tasks you can work with. So in much more simpler machine learning construct, you have what we call classification, and we have what we also call like regression. So let me just mute this sound that's coming in. Yes. So yeah, so you have like classification and you have regression problem. So in classification, what primarily is classification is what you say it's like categorization. So you want to categorize in which particular class or label an example or an input is. So think about it in a way in which, let's say you have some
43
ina takardar
wace takarda
da na ba a ba wannan ba
17400
to da babu wanda
sorry, I just want to mute everyone. Okay, so think about it in the case you have you want to classify between like two particular, perhaps cat and dog, and you see an image of some nice looking cat. So here, where will you categorize it? In which particular bin will it be? So you want to classify it between either like a cat or dog. So that's like primarily what you term as classification. So here it looks like a cat, then you bin it into a cat. So that's like classification. Whereas in regression, what you want to predict is a real value number. So it's a number. You are not categorizing anything. You want to predict some kind of value. So let's say you're building a model for stock market prediction. So your market takes an input from anywhere. It could be from the internet. It could be some value you provide to it. And based on that input, it performs some manipulation on that input and get some value. So you can think about it like, let's say some simple regression line here, where you have some input X and you have your output Y and you have some sort of function here. So for each value of X, you get a corresponding value of Y. So your value of Y is, let's say it's like a floating point, it's a real number, so it can be any number. So that's regression. So there's a difference between regression and classification. So to just solidify your learning, so I'll just want to quickly show us an example in which you will help me solve here. So so as we said, classification is majorly about like categorization. So how can you categorize some items or classify them into where it should be? So, and we will like solve this problem and also think critically on how our machine learning model will be able to solve this problem for us. So let's say we have two bins here. Let's say this is a cat and this is a dog. So I just want you to help me on the charts. Can you perhaps tell me which is a cat or which is a dog so that we can put it in the proper bin it's supposed to be? You can type on the chart. So from these images, which of the images do you feel is a cat and which is a dog? So there are some answers coming in. Yes. So there's Mariam, she said 1, 2, and 3 are cats, then 4 and 5 dog. Okay, that's nice. Any other answers? There is Amalai also. Yes, so 1, 2, and 3, yes, they look like a cat. And so let me just put them here. 1, 2, and 3. Then 4 and 5 are dogs. So yeah, thank you so much for your kind response. So as you can see here, what you have helped me done is to classify these animals into cat and dog. So that's like majorly what's known as classification. So any problem you kind of encounter in the future, it's doing this when you try to divide the problem into like subsets, which belongs to where. So that's classification. So in this particular example, you can see we are classifying into like 2 distinct categories, 1 and 2 here. So this is what we term as like binary classification. So because they are like 2 particular bins, you are classifying into 2 categories. But if you have more than 2, so it's what you call like multi-class classification. So that's it. Then you have something, well, I will get into that. We'll talk about that multi-label classification. We'll briefly talk about it. So here, again, relating to machine learning, here you've easily identified a cat for us because you've had experience of seeing cats several times and you have experience of seeing dogs several times, and your brain has built in like some feature detection of when it sees some particular feature of the cat, you know it's a cat, but your machine learning model doesn't know that. So what we want to do, particularly in this particular class, we don't do exactly train identifying cats, but classification in general, so that when your machine learning model sees some particular data, it can know where to classify it to based on like the examples you've provided it with. So that's one. So if you look at 3, so I'll just talk about some examples. You look at 3, there's no face of a cat, but you were able to identify it's a cat. Why was that? Because you've seen some interesting features that are related to the cat, likely the fur and perhaps the shape of the hands. So you build some kind of system, not only with the face. So we want our also machine learning model to also learn to work with that as much as possible. Then interestingly, there's number 4, which is also a dog. So you were easily able to pick it out as a dog, even with the glass and everything. So this shows you like your internal classification systems of recognizing animals is like perfect. So we want our also machine learning model to be able to distinguish on these classes, even though if there are like some obscure items on it, or even though the images might not be as complete as we want it to be. So with as little features as possible, it could be able to do that. So that's the kind of like idea about classification. So we can continue quickly on the lecture. But feel free to ask any questions if you want on the chat. So I'll be there to answer a few of them. Yeah, so we have multi-class classification, we have binary classification, we have multi-class classification. As we explained, if you have like 2 bins, you are categorizing your input examples into 2 categories, like we just did in the exercise, cat and dog. So it's binary classification. If you have multiple categories, let's say you have cat, dog, panda, elephant, so it's more than 2. So it's multi-class classification. Then we have what you call multi-label classification. Assuming an example is assuming you have a news, let's see, some news, maybe newspaper, it can be from anything, it can be a newspaper, it can be like an article online, it can be a Twitter post, and we need you to classify it for us into several categories. Maybe 1, we have maybe healthcare, let's say technology, let's say business. So let's say an article that talks about, let's say VR for medical patients or for doctors. So you can see it falls under health and it falls under technology. So by VR, like virtual reality. So the virtual reality is technology and it's used in the healthcare space. So it's like health, but it doesn't talk about business. So that's like 0. Then if you look at an article about maybe, let's see, the salary paid to like a sports footballer, like a very high amount, and how it affects the business of the club or something. So you can say it doesn't talk about health, it doesn't talk about technology, but talks something related to business. So you see here, it can, so each of the news are coming, so it can fill more than 1 category. So it can fill like the category for health, category for technology or business. So that's what we call multi-label classification. So you just don't bin it to 1 particular category, it can exist in multiple other categories. So we'll just get into this. So for this particular problem, we'll be attempting to solve the binary classification. And hopefully with what you learn, you can also apply to multi-label classification and also multi-class classification at the end of the day. So feel free to ask your questions at any point in time, and happy to answer them. So as always, I will just skip to the main parts of what we need to discuss so that we can discuss them more. But if there's anything I missed that you want to learn about, just feel free to always let me know. So as we've always talked about in the machine learning pipeline, what you always need to do is like you get your data. Once you get your data, then you kind of build a model or look at an existing model in which you can use, then fit that model to the data that you have. And after that, you evaluate how well your model is. If it's good to your satisfaction, has very good metrics, then you can maybe save the model for offline use. But if it's not, then you do some kind of optimization, some hyperparameter search as much as you want to improve on the model. So at the end of the day, if you have a very good model, then you save it. So there's a question from Bello. Feel free to ask your question either on the chat or like you can
Good evening,
voice it
sir.
out.
Thank you very much. A
Yes.
very quick one. My question is respect to the last class.
Yes.
The output you gave was a kind of linear function. So if you want to build an output that is not linear, like in the case of neural and other things, is
Hmm.
this the same thing that will impute?
So if you want to, so I'll quickly answer this. Like if you don't want to build a linear function, so that's where you have to use activation functions, and which we will talk about in the later part of the class. So if you
Yeah.
don't want it to be linear, yes. So don't worry, we will get very deep into it, and you get to understand the effects of activation functions and how it affects training of your
Okay.
models.
Thank you.
Thank you for the nice question. Yes. Yes. So just move on. So first, as important as possible, so you need like your architecture. Don't worry about this. We'll talk this in details when we get into the model. I will explain each of these key parts so that you have a better understanding about it. So first and most important, we get our data set. So here the data set is like perhaps almost like manually created. It's data set of cycles. Then don't worry, we'll get to visualize it and you get to see it better. So here it's more of like just getting a data set you need. Here we just need 1,000 samples of data with some bit of noise. And we have like a random state here. So in the last or first class, we talked about like how to generate random numbers and what is the random state. So here, the random state is very important here for reproducibility. So when you set your random state to some value, anytime you call this function here, make cycles, let's say to generate data. So it generates the same amount of data or the same type of data with the same values every point in time. So this helps you a lot because let's say you don't add this number here. I will still explain this later on. And you get to build a model with some particular kind of data set. And let's say it has a good performance and you save that model and you send the data set to me or to any of your colleagues. So what will happen is when I want to try out the model, it might not have as much accuracy as you claimed it had been. So I might begin to have some doubt, or someone begin to have some doubt. So, but when you set this random state, no matter anytime the person like generates this data, it will always have the same data as much as possible. So someone has like a question about noise. So noise just simply means, let's say, for instance, you are looking at some data points here. So let's say the data point is supposed to represent like this value between X and Y. So when you put some value for the noise, so it doesn't like, so ideally it should like pick some data points along this line, but it might just pick away from this line. So it's not exactly on the line itself. So that's like the effect of noise. So when it's a higher value, when you put it to 0, so it will exactly on this like red line. But when you put it to some higher value, so it will deviate from that red line. So in most cases, you want to add in noise because at the end of the day, when you build your model, the input that will come into your model, it's noisy. That's real world examples. So assuming you want to build a classifier for cats and you go online and you check really nice pictures of like cats. So, and you put it and you train your model. So at the end of the day, when you save that model and someone wants to use your model to perform some inference or test out your model, the image of the cat that it will put in, it will be like a bit like weird, or maybe you see the cat standing on its head or something. So it's a bit different from the data you change it. So sometimes it's good to add noise in your incoming data and in your machine learning pipeline, but you come to see more about how this noise affects training in the subsequent lectures, inshallah. So yeah, thank you for the question. Yeah, maybe I'll hold on the question on the outlier and the noise. So on the noise, it's particular to the implementation of the data sets. So I would say for the noise, maybe this is from the skline data set. So if you want to check it out, you can definitely check on the documentation for this. So you can just Google it. But I honestly don't know how the noise, but it's like from 0 to some kind of certain values. When there's no noise, it's like perhaps a perfect cycle. So, but when there's noise, the cycle like kind of deviates. So yeah, but I think if you understand the general concept, so is it the same with outlier? I wouldn't say it's the same with outlier. So outlier is more of like you have some data of some particular maybe range or some, it deviates a lot from your expected data. So I will quickly, so here we've generated our data. So what we need to do next is, yeah, so here's just some analysis. If you have some machine learning background, so you can just see what's the distribution of your data. So it's always good to visualize your data. It gives you a feel of how your data is. So as you can see from our data, it's supposed to be a perfect cycle, but you can see some values are a bit like outwards a bit. It's not as perfect as we want it to be. So that's the effect of the noise. And a more higher noise, you get like a much more like cycle of higher disturbance than this. So this is like good. So what we want to do here is to classify between the blue and the red lines to identify them between one another. So for each example that comes in, if it lies around, let's say in the blue region here, to classify as blue, if it lies around the red region here, so it's classified as red. So that's our task for today, which we will go through. So as always, you have your input, and your input consists of data of one chip, 1,000 items, and here you have 2 here. This 2 here just shows you like the number of features. If you're from a machine learning background, it just shows you the description of, this 2 here is the description of your data. Let's say you are dealing with some data of, so here simply it's like your X and your Y here. So your data has some X and your Y value. So it can be like 0.5, 0.3. So this is where your 2 comes in. So it just describes your data. This for the first one, maybe the second one, then the 1,000th one had its own values. So that's features. But if features is not clear, I can explain what features. It's just the general machine learning term for features. Yes. Yeah, so I will likely skip some questions, but don't worry, I will get back to them after the class. Thank you. Yes. So here's just some maybe analysis. So as always, like you get your data, so you need to put it in the tensor format. So as you know, we are using Pytorch to build our machine learning model. So everything needs to be like in the Torch framework. So what we do here, so no matter the data format of your data, you can move it to Pytorch. So here our data format is NumPy. Then what we are doing here is Torch from NumPy to move our data from NumPy into Torch as a tensor. So once we run that, we have a Torch tensor of our data, which we have here. And you can see we have, for the labels, we have like 1, 1, 0. So for one class is 0 and another class is 1. So as the typical machine learning, you need to divide your data set into your train and your test. So to see how well your model is performing on the train and test, to test for underfitting and overfitting. So these are familiar with you. So we'll skip into the model building part, which is like one of the most crucial parts for this particular session, to see how a model is being created. So you've created models in the last session, which is like a linear classification model. So, but for this, it's a bit different. So here, what we, as always, will import our Torch module, which we use for our PyTorch. Then here, as you remember, you can either choose your CPU or your GPU. So your GPU here is like an accelerator. So it helps you run things very fast. So you check if it's available on your machine, then you select it as your device. So here in my Colab, I have CUDA available. So it tells me like I have some GPU resource available, which is like T4 here. So it depends, but don't worry, for this exercise, you don't need any GPU. So it's not like some really intensive tasks. So don't worry too much about that. So let's see. Yeah. So what we want to do next is to create our model. And I'll just explain what this is. So this is our machine learning model. So as always, in deep learning, what you have some data, X, and you want to learn a model here that will map X to Y, that will predict it really well. So think about the cat example that we talked about. You have an incoming examples of cat, and you want to build a deep learning model that will learn to like classify cats as cats and dogs as dogs. So here, it's the same. So we want to categorize each point that we see on the cycle as either a red dot or a blue dot. So here I want to create that model that will help us do that. So as always, you want to import for your n dot model. So as we said, think about like a laboratory that will help you create your neural network. So once you want to create any model, so you inherit from that class. So it gives you all the necessary tools that you need to build your neural network. So for the initialization, we want to create a neural network. So what happens, as we explained, this is like your initialization. Once you call this method here, or this class here, cycle model, so it first initializes this. This is like the very first thing it creates for you. Then when you want to do your forward computation, then it runs this. Then I'll briefly explain this over again. So here, what happens is when we want to create our model, here we want to create a model with 2 layers of neural network. Think about it this way. We have our okay. So we have our data, which has like X and Y. So it has like coordinates of X and Y. So as you remember, the coordinates of X and Y are just, so let me see. So it has your coordinates of X and Y, which are your features. So they are like the 2 inputs coming to your model. And at the end of the day, you want your model to use those 2 inputs and make some prediction. So what we want to create here is a neural network that takes in, don't worry, I will explain this to you. Yes. So what you want us to do is you have the first layer neural network. So the first layer of your neural network is supposed to take in the input of your model. So, and you know your input has like two features, which is like the X here and your Y here. So you want your X here and your Y here to go into the model. So it can be X goes here as the input and your Y goes here. So this is layer 1 of your model. So you can see we have described our layer 1 here of the model here. So from the graphical illustration just above, you can see layer 1, you call like the nn.linear, which is like a linear, it's just a linear layer. So you tell it should expect an input of 2 and output of 5 here. So that's what we just created for our model. That's for the very first layer. So an input of 2, which is from our original input, comes in and outputs 5. Then for the second layer, here, what we are telling it, like, should expect an input of 5 and output of 1. So this is like the final output that we want of our model. So when this happens, your input comes into your layer 1, then it goes to your, let's say, layer 2, and you have a final output here. So if it's not clear, feel free to ask questions, happy to answer them. So that's how, like, so in each layer, you can specify how many neurons it has. So the first layer, it has 2 neurons. And from the second layer, it has like 5 neurons. So for the very outermost layer, you want it to have like just output of 1, because you want to predict if like yes or no, is this like red or blue? Is this red or, yeah, is this red or blue? So come to see how that comes into effect. So here in your forward function, what you are doing is any input that comes in, X here, which can be like any data. Let's say you have 1, 2, 3, up to 1,000. Let's say this is 0.5, this is 0.1. So let's say any input that comes in, it goes to your forward here. And what you want it to do is pass it to layer 1, then get the output of layer 1, then pass it to layer 2. So anything that happens, return that. So that's how it happens with neural network. As you can see graphically above here, let me just cancel this a bit. So as you can see just above here, so your data comes in here. So your data comes in here, it goes to your layer 1, then goes to your layer 2. So that's exactly what we are interpreting in this forward function here at the end of the day. So hope everyone is good with this. So there's a question from Bello. What are the possible outputs of layer 2? So the outputs of layer 2 are any values from, let's say, maybe negative infinity to positive infinity. So that's the value because they are all floating point numbers. So here, think about this layer as this layer 1, think about it like corresponding to having like, 1 minute, let me just see. So your layer 1, it has like its weights and maybe some bias. Let's see. So your layer 2 has something similar, like your weight and also another bias. So remember your linear regression model, like you have WX plus B. So think about this. So each of the layer performs some similar operation to this or same operations to this. So when an input comes in to layer 1, oh, rather, let me see. I think I'll be able to explain better here. Give me 1 minute. Yeah, perfect. So here, let's say we have your input of data coming in. Just clean this. So which is like X and your Y. So what you want to do is you want to get an output of maybe the weight times, let's see, X and Y. Don't think about too much of the notation and the bias here. Then here you have like the output of, let's say, layer 1. So which has some values of like 5 here. So for, okay, let's say layer 1 computation. So this is the computation that happens in layer 1. Then the output of layer 1 goes into your layer 2. Maybe it has its own weight. And you have like the output of layer 1, then plus like the bias here. Then this is the output of layer 2 here. So which has just one value, because as you specified here, oh, it's a bit. So as we specified here, just kindly bear with me. As we specified here, we want the output of layer 2 to be 1. So hope that's clear or not too confusing. Yes, so there is. Okay, thank you, Bello. So can we use NN parameter instead of NN linear? Yes, feel free to, yes, you can use NN parameter. So, but NN linear makes it easier for you. But NN linear also is like a parameter also. So NN linear just represents, this equation here. So just represent this let's say X plus B here. So just like a simple approximation of your WX plus B here. So that's your NN linear. Yes. So you can, if you want to like create your like WX plus B from scratch, then you can use your parameter. But NN linear is also a parameter. Yes. So I will just, so that's how you do your model definition, but we'll come and see like there's other simpler ways of doing your model definition next. So let's quickly, so here we've created our first model we want to try. And yeah, we'll see what is the performance of this. So this is just showing you like there is this playground of TensorFlow. Then you could play around with the neurons. You can add or reduce neurons and add some activation layers and see the effect. So I would advise you may play around with this and see how the number of neurons or number of layers affects the performance of the model. But that'll be like in your free time, you can try this out. So yeah. So as we said, like this is, we explain how to create this model. So this is like some general way of doing it, but there are much more simpler ways of creating the model. So, and I'll tell you why this is okay and where it will not maybe be sufficient. So here you can create similar model as we created above using this nn.sequential. So nn.sequential, what it does is telling you for the next coming inputs, it's a sequence. So it's one after the other. So what is telling what we are telling it is we have like our layer 1 here is first, then our layer 2 here is second. So like for any input coming in, first it will come to layer 1, then go to layer 2. So that is the meaning of nn.sequential here. So it's telling you the layers should be in sequence, which is good and easy because for simple models, it works fine. But when your model gets super complicated, it becomes like difficult to handle. So imagine where you have a much more complex model like this. Just give me 1 minute. Yeah, the input comes in here, but also goes here. So, yeah, so this happens usually in like your resonant architecture, which you will come to see in the maybe next 2 lectures. So this is a complicated architecture and you can't use this in your using this nn.sequential because as you see here, it's not sequential in nature because your input comes to layer 1 and same input jumps to layer maybe 2. It adds up with the output of layer 1, then goes to layer 2, something like that. This is much more complex. So that's when you need to default back to this particular method of creating the model. But for some very simple models, you can use nm.sequential, just telling like for each layer, it comes like the input comes in and goes to the next layer. So feel free to ask questions if there's anything that is not clear, and we'll get to see it. So right now, we'll just go straight into building the model. But before that, let's look at some like loss functions we use and also like some optimizer. So here, like as we discussed in the previous lecture, think about loss function as a map. So it tells you like how good or how bad you are doing. We gave the illustration of the map of Nigeria. Let's say if you are starting from Kaduna and going to Lagos and you move up north, so it will tell you like your distance is far away, and when you move much more towards the right direction to Lagos, then you reduce the distance. So depending on the loss, you get to see how well your model is performing, and your model use that to update its parameters or internal state. And we talked about how the optimizer is like a steering wheel to tell the model, like you're moving the wrong direction, let's go this, or move right, move left at the end of the day. So optimizers, you can use almost any optimizer for classification problems. You can use either the commonly used one, the stochastic gradient optimizer, or the Abdam optimizer. So don't worry, we'll get much more deeper into this, but if you want more explanations, we can explain or talk about them. So just take them, it's like a steering wheel to help you improve your model. Then you have a loss function which tells you how well your model is performing compared to like the real values you have from your data sets. So for simpler classification problems, that's like for binary classification. So what you want to use is the binary cross entropy loss. And for much more, for let's say, when you have more than 2 classes, you want to use cross entropy, like for multi-class classification, you want to just use the cross entropy loss. So, but this here, when you use it, you can also use it for binary classification. It just defaults back to like the binary cross entropy loss. So this is much more of like a general formula for like any model for 2 or more than 2 here. So just feel free to use any. And if you want any information, you can always check this, like we said, you can always check the documentation and see what is what it takes in and what it does. So yes. So that's for classification problem. So for regression, it's a different problem. So for regression, you want to look at like the mean absolute error, the L1 loss or mean squared error, because these are generating like real values. So for multi-label classification, yeah, for multi-label classification, you can, yeah, that's a nice question. Yeah, honestly, don't know for multi-label classification. I think for multi-label classification, you can also use, Yeah, for multi-label classification, you can use cross entropy loss. So it works well, yes, for multi-label classification. But I'll confirm, but highly guess it also works for multi-label classification. That's the cross entropy loss, yes. Yeah, thank you. Yeah, so now we have our model, and so we want to do one. So let's look at our model again. There's just one more thing. So with the binary cross entropy loss, there are like two variations. There is this one with logits, and there's just binary classification. So I'll briefly tell you the difference. So, but let's look at our model. So remember our model, we had this. We have this 5, and we had this 1. So this value here, just give me 1 minute. So let's say your input comes in, it goes from layer 1 to layer 2 up to the like final layer, and you have like 1 neuron, so it generates like just one value. So the range of this value is from, let's say, negative infinity to, let's say, positive infinity. But this value is a very wide range. So what you want to do is to compress this value to something very small, to like some kind of probability distribution. So how will you do that? So that's where activation function comes into place. So we have this, I'll just go into it. We have like sigmoid, we have several activation values. So one common one to convert it from this. So this is the range of your output at the end of the day. I think there was a question about the range. So the output of your model would range from negative infinity, that's a very large value, to like positive infinity, can be any value. So, but once your model predicts that, so you want it to be bounded within some range, because we want to know if it's orange or if it's red. So we would say, assuming based on the data set, it can be red is 1, and let's say blue is 0. So, but here it's giving us negative infinity to positive infinity. We want to change that from this to this 0 to 1. So how would we do that? So that's where activation function comes in. So one popular one you can use is like the sigmoid activation function. So I will briefly show you what it does in a minute. Yeah. So with the sigmoid activation function, it's just like some mathematical function. So any input that comes in, it transforms it between 0 and 1. So you can look at, so we can say from maybe negative infinity to positive. Yeah, let's see, you have 0.5 here. No. So you have something of this nature. So this is probably, yeah, 0. So anything like greater than 0, it starts to give it like a value of more than 0.5. So anything less than that value, so it gives it like much more lower value. So the value is ranged from, at the end of the, any inputs that comes in here, in your maybe X or your Y, so the final output will be range of 0 to 1, which is more of like some kind of maybe probability distribution. So between 0 or 1. So if it's, you can say if it's 0.5, more than 0.5, so it's very likely it's a red. So if it's less than 0.5, it's not a red, it's a blue. So that's like one way to look at it, yes. Yeah, let's go back. So yeah, so that's the effect of sigmoid at the end of the day. So in these two particular loss values, this one here, applies the sigmoid for you. So you don't need to apply it yourself. You don't need to put in your model. So you just put in like the value at the output of your last neural network. You just pass it to this loss function. So it applies the value, the sigmoid for you. So it's within this particular binary cross entropy loss. But this it doesn't have the sigmoid. So you have to like put it in your model. So depending on what you want to do. So as you can see in our previous model, we don't have like the sigmoid activation function. So we would choose to use this so that it will like apply the sigmoid for us at the end of the day. Yes. Yes. So yes. So let me just, yeah. So here we are using this because it has like sigmoid inbuilt, and you can run this. And so one metrics we want to use accuracy, how well the model is predicting the values. So out of the total of perhaps, let's say 1,000, how many is it getting correctly with accuracy? So here we'll just, yeah. So I will also skip here. So what does, yeah. So here, as we said, the output of your model would be like from negative infinity to positive infinity. But because we have the sigmoid here, it will be from 0 to 1. So here I want to enforce if, let's say, the output of the model is, just give me 1 minute. So let's say the output of the model is 0.5, then we can say it's a red dot. But if the output of the model is less than 0.5, we can say it's a blue dot within the cycle. So that's what we want to enforce at the end of the day. So this 0.5 is just arbitrary. So it can be, you can choose some other values if you feel, but I think the standard is 0.5 at the end of the day. Yeah. So let me just clear this. So here we just train the model we have. So we have gotten the data set, we have built the model, and now we've set in the necessary tools we need for training. Then here, as I think we've explained this in the last session, so no need to go over this. So we'll just train to see how it goes, but feel free to just stop me if there are any questions. So here, as you can see the metrics, the loss looks good. It starts like quite low and starts declining, but not declining so much. So it's good to measure like how the loss starts and goes, but you can see it doesn't change as much as possible. That's for the training loss at this very first column. So the accuracy, you can see it's like between 50, then it starts dropping, like it's not learning anything at all. So that's even for training. So that means even for training, it's not learning anything. So for tests, it's maybe better. And when your model in training, the test is better than the training set, you know, there's a very big problem. So you need to look into what you need to do at your model. So there are several things to do to improve your model performance. So here you can see it's not learning as much as it's supposed to be. So you can see like the capacity of the model is not enough. So what we mean by capacity is like, let's say the size of the model is not enough for it to learn it's not enough for it to learn the distribution of the data. So you can do that by either adding the number of layers or adding the number of neurons. But there are no clear-cut ways to do that. You just experiment and see how things are, or you change adding some activation values. Yes. So here we can see it's not performing as much as we want. Then we want to like improve it by adding some changes in it. So, but first, let's visualize. So as we said, visualization is very important. So you can see what our model is doing is much more like a linear classifier. So just drawing a straight line, and this is a cycle. So it's impossible to separate between this red and blue dots here with just a straight line. So no matter how you do it, so it will be just on average 50. So the same goes for also the test sets. Yes. So what we want to do is to improve the model. So no matter, let's say, you can improve the model by adding much more linear layers, but at the end of the day, it will still be a linear layer because like when you sum up like several linear layers together, it still give you the same linear layer. So it won't really change anything. So no matter the number of linear layers you add to this model, so it will still be a straight line. So it won't give you as much effect. So one trick to do which will help improve is, I'll just go straight to the point, you can all read this later on. So it's to add like activation functions. So as you can see here, the data set here is, yes, here SVM would like work good. So, but Yeah, so SVM has some like internal non-linearity, but for neural networks, they're all like linear, so you need to add in some non-linearity. So one non-linearity we have already looked at is like the sigmoid activation function, but there are like several other ones which one could add. So I would just keep this. This might not help a bit. Yeah, so this also, they try adding more layers, but it didn't work out. But I just want to go straight into, and I briefly explained it. So just to give you a better perspective about that. And let's give me 1 minute. Okay, like this. Yeah. So one thing we can do is add non-linearity. So there are several non-linearities available. So what non-linearity does is, assuming your output is just supposed to follow some straight line, so it gives it some kind of different distribution so that it will learn better the patterns, because not everything is linear in nature. So as you could see, like the cycle, so it doesn't follow like a linear pattern. Let's see the cost of house and the size of the house. Maybe the more expensive the house, the much more bigger the cost, the much more bigger the size, and the reverse. But in cycle, just like it's just there, it doesn't follow that pattern. So you want it to kind of follow the pattern of the cycle. So that's where you add non-linearity. So they are of several types, and we will just briefly look at them for the sake of time. Let me see. Yeah. So here we still go creating our same data. Then yeah. So this still the same. So one non-linearity we have here that we can change to our model is ReLU. That's rectified linear units. So what ReLU does is, let's look at this. Let me see. Let's say you have your X and your Y. And can I just draw this? And let's say this is your 0 point. And you have perhaps some straight line here. So what ReLU does is, if the value is, so this is, yeah. So if X is less than 0, then the output becomes 0. If X is greater than 0, yeah, then your output is X here. So anything coming in, if it's less than 0, it's like 0, like it kills it off completely. But if it's more than 0, it retains that value. So let's say for this red line here, so if we are using ReLU, it will still be like, since here is greater than 0, it still follow the same pattern, but this is less than 0. So you can see like this is 0, this is maybe increasing, and this is like some negative value, maybe some negative X. So it's less than 0. So what ReLU does is like it kills it off to 0. So here you've added some non-linearity, because you see for some values it will be 0, and for some values it will still have the original value it has. So that's one non-linearity. And there's a sigmoid we talked about. There's like the tanh one. So you can explore these activation functions and to see their different patterns. And it might also be worth knowing their formulas just for helpful sake at the end of the day. So I will briefly come to your questions in a bit. So let's just quickly run this and see what performance we will get. And yeah. So as you can see, the model starts like quite high, 6944, similar to the past one, but it gets much more lower. That's 0.67 than our previous experiment. And it's improving from 50% and to 58%. So as you can see, it has improved. And also the same for the test. So it's also improved, and it's not like just 50 and going low. Then, yeah, just one quick one before. Yeah. Yeah, so that's like the effect of activation function. So, and if you train for more epochs, so the more better your model will get. As you can see, it's increasing, the accuracy is increasing. So the more longer you train, the better it gets. Yeah. Then here we can briefly evaluate the model. Save something. Okay. That's model 3. Yeah. So this is like the curve of the sigmoid, as we just explained. And this is that of ReLU, which we just talked about briefly. So just give me 1 second, another one. Okay. Okay. Yeah. So yeah. So let me just run this and we quickly. Please don't scribble. Yeah. Thank you. Yeah. Yeah. So that's majorly it. So here, let's briefly look at like the performance of the model and see how it does. Yes. Undefined. Yeah, but feel free to ask your questions while I just sort this out because I skipped some cells above. Okay. Yeah. So yeah, so as you can see, like for the very first model we created, it doesn't have a non-linearity, and you can see it's just like a straight line all through. So since this is a cycle, so no matter the number of layers you add in, so it will just be like just give you 50%. So because it's always like a straight line just cutting through here. So but when we added non-linearity in the subsequent model, so you can see it has some, it kind of tries to assume the shape of the distribution of the cycle to categorize them as much as possible between red and blue. So where you have, even though it's not perfect, so but probably when you train for much more longer step or epochs, you get like the better classifier to classify between red and blue. Yeah, so that's majorly, I think for this particular class, we looked at like classification, and you also saw the effects of activation functions, which you will come to use like as much as possible in your subsequent class. And even in general, when you want to build like very, very massive models. So I'll just briefly go into like the questions and see some questions that I missed. Yeah, so there is a question, is there a situation where ReLU is better than or preferred over sigmoid or vice versa? Thank you, Bala, for the answer. Yeah, so yeah, nice. Yeah, okay, let me see if there are any other question. So let's see, one good way to look at like sigmoid, if you are doing binary classification, it's always at the very final layer of your model. So it's like 0 or 1. Then ReLU is mostly like within your layer itself. So, and one issue with ReLU, you can have like very vanishing gradients when you are training like some natively large model, because as you can see, like it kills off some values that have negative, maybe some negative values to 0. So when you have several of those 0 in your when training your model, so it becomes a problem. Like your gradients become 0, there's no change in your model won't learn anything. So one will have to like look out for better ways. So there are like much more better modification to ReLU, one which is like leaky ReLU. So we didn't look at it, but you can maybe try it out on your own and see how it goes. Then yeah, I believe. So I guess we've answered most of the questions. And yeah. So but if there's any, feel free to unmute and happy to answer them. Yeah.
Hello, sir.
Yeah, hello, yeah.
Thank you very much. So I'm looking at this our data set that has
Yes.
blue and red cycles. So
Yeah.
how about idea of using a mathematical transformation? So you transform this data set into a higher dimension where you could have a separate regions for the blue cycles and the red dots, and then easily use linear classifier or something like sigmoid, and then after running your models, then you go back to your original problem. Is that possible?
Yeah, I believe it's quite possible. It's quite possible. But I think because one of the challenges with, let's say, when you want to use mathematical transformation, you introduce much more complex things. But here with neural networks or deep learning, let's say we don't want you to have like an idea of maybe the mathematical transformation. Like you give
Okay.
it the data and it learns that pattern itself. So that's
Okay.
like one of the selling points. People call it a black box. So it's just like you passing your data, and at the end of the day, it kind of learns the patterns for you within those data. So, but it's also nice. One could try those transformations, but with like deep neural networks, you want it to internally like recognize those patterns itself. So that's one thing, even though like those patterns can be explained or not so much. So that's like black box, and that's where maybe one would need to go into like explainability, what the model is doing. So, but the idea of deep learning is, yeah, it learns internally like those patterns for you. So because when you want to design something external, like those higher dimension, so it becomes maybe too complicated for you and you don't want to go through the maybe
Okay.
route, maybe for very, very high complex problem.
Okay.
So, but you just like, you have your data and you pass it to your neural network, and maybe you just specify some dimensions of the neural network and some configurations. So it helps you like identify your problems easily.
Thank you.
Yeah. Yeah, thank you for the very great question. So yeah, so it's so that's like so that's the end of the session. So please be mindful of your emails and like Discord. If you're not in Discord, please join the Discord. And just one last thing, we have so we have this email. I know if you've submitted your, what's the name? The assignment, you must have received some review. If not, you'll be receiving before maybe before Monday. So please be mindful of submission. It's very important. And because if you don't submit the assignments, especially on time, so I know the first few weeks were a bit rocky, so I think there won't be much problem. But if you haven't submitted, please submit as early as possible. For the subsequent submissions, there would not be maybe late submission entertained, except that with valid reason, please. So, but please try to like submit the assignment and do them, because it helps you solidify what you've learned in this session. Then check your emails also. So there's this email we have which you will receive your reviews. But if you haven't, yeah, don't worry, it will come to you. So, but if at the end of like next week you don't get it, just email us back. So for anything important, just use this email, forward to us, we'll see it and we'll respond, inshallah. Then yeah, so send the reviews. So if there's anything, talk to us on the Discord channel, inshallah. Then what again? Yeah, the assignments, just keep up. I think nothing new. So this is majorly it, and it was really nice like talking to you this evening. So if there are any questions, feel free on Discord, and the TAs who have been very helpful, especially with your grading. So we'll be happy to help, inshallah. Yeah.
So, sir, one last one, please.
Yes,
In the
please.
first class, you made mention of GPU and how it not paralyzes. You mentioned something of parallelism in
Hmm.
terms of computation. It
Yes.
performs better than the CPU. So, for instance, is it you that will assign what you want each of the core to do to you, or it will be done internally by the computer itself?
Yeah, so how it happens is, yeah, so that's like why it's important, why I want you to learn the Pytorch framework. So it does like much more higher level abstraction of what you need to do with this GPU. So, but you can tell it like, let's say you have several GPUs. It's more of like you have several laptops with GPUs. So you can tell it maybe this part of my model should be on this GPU and that other
Okay.
part should be on GPU too. So you can tell it
Okay.
to do that for you. So that
Okay.
would like wants us to go into like distributed system. So, but like
Yeah.
on a higher level, like you can specify what you should do, but on lower level, PyTorch will handle everything for you.
Okay.
Yes.
Okay.
So if you want to do much more optimization, so you have to go like deeper and deeper into like the stack of like touch and see like where it's going to where and what to do. Yes. But on a high level, like PyTorch handles most things for you. And
Okay.
let's say if you're training like very large model, let's say like ChatGPT 4 or ChatGPT 3, that's like
Yeah.
around, I don't know, like 175 billion parameter, so it can fit into one GPU. Then you can have like multiple GPUs. Either you do like some pipeline parallelism or some tensor parallelism and just mix that and do that. But that becomes complex, so you need to handle like what goes into what partition and that. So, but on a high level for like the models we build, so Torch handles it for you, so you are good to go. But for much more extensive stuff, so you need to define what it will do.
Thank you, sir.
Yeah, thank you very much. Yeah, so it's nice. So I hope you do have a lovely weekend, inshallah. Yeah, thank you. Bye. Yeah, thank you.